Hello everyone. So in this session we'll study and we'll learn about Bode plot under frequency response. It is the part of control system engineering. My name is Hari Mohan Rai. So let's start with the topic. The first we'll see steps to draw Bode plot. I mean how we can draw the Bode plot means a very easy way. So let us have a short look. First of all, we'll take the transfer function GFS, and similar to the polar plot, I will put S is equal to j omega in the given transfer functions. Now, Bode plot has two parts: magnitude and phase plot. Actually, in a similar semi-log graph sheet, we'll plot both magnitudes as well as phase plot. So first of all, we'll see the magnitude plot. So under magnitude plot, the first step is to find the corner frequency. We'll we'll later discuss about what is corner frequency. Then after we'll draw a magnitude table that will decide that slope and all those things of that uh, plot, and then we'll choose the lowest and highest frequency apart from this corner frequency. Then we'll find out the magnitude at each corner frequency, and then we'll go for the next step like phase plot. In under the phase plot we'll again find out the phase, that angle of the given transfer function g of omega, and we'll put the value of omega corresponding to that uh, values of g omega, and we'll correspondingly we'll find out the angles, and then after we'll draw the Bode plot on a semi-log graph papers. So here we'll start with the again example, instead of more explaining the steps, we'll see the here practical examples. For Bode plot example one, I have taken a type 1 system for your convenience or for easy purpose. Now we have taken transfer function g of s is equal to 1000 divided by s into 1 plus 0.1 s and 1 plus 0.001 s. Okay, we'll start with the first step. Put s is equal to j omega, and it will become g of j omega is equal to 1000 divided by j omega 1 plus 0.1 j omega into 1 plus 0.001 j omega. Okay, so this is the first step. Now we'll start with the magnitude plot. First we'll draw the magnitude plot, then we'll go for the phase plot. So in magnitude plot we'll first of all find out the corner frequency. The corner frequency is actually the frequency where the slope of the response or graph changes. For example, like we have the term s here, three s terms are there here, individual s terms here, s terms, and here also s terms. So the corner frequency will changes always when it will have the form 1 plus ts, like that, or you can say s plus t or t plus s, like that, where t is nothing but time period we are talking about. So here, I mean, in this case we have only two corner frequency because uh, there is only two terms which is in the terms of 1 plus ts. Okay, so how we'll find the corner frequency? Now look at here, we'll find out the first corner frequency, second corner frequency. Just you have to uh, be sure that while finding out the corner frequency, the lowest corner frequency, I mean the corner frequency which have the small value will be the first corner frequency, and the which will have the comparatively larger value will be the second corner frequency, and so on. That means it should be in ascending order. Okay, so what we'll do, we'll look at here 1 plus this part will nothing but t, and this is s which we have replaced by j omega. So omega c1 is equal to 1 divided by this constant, I mean 0.1, and it will become 10 radian per second. With omega c2 is equal to 1 divided by this, now this constant 0.001, and it will be nothing but 1000 radian per second. So this is radian per second is the unit which of the frequency which you have to take. Now note, look at here, now to find the corner frequency we make sure that our transfer function is in the form of 1 plus t. If it is not, for example, if it is in terms of t plus s or s plus t, then you make it in the terms of 1 plus ts, like after taking t common, so it will become, yeah, s common, it will become something plus 2s. For example, there is a term s plus 2. If you are taking 2 as a common, so it will become 1 plus s by 2. So s by 2, that means 0.5 s. Okay. And if again after finding after completing in the form of 1 plus ts, you will find out the corner frequency, which is nothing but it is corner frequency will be equal to 1 by t. uh, if you are finding any difficulty to determine the corner frequency, for rough work you don't have to mention in it in your solution. Just for rough work I am telling, because this is not an exact procedure. Just to make you remember, what you do, you take the uh, terms is equal to 0. For example, if you are taking j omega is equal to 0, omega will be 0, so there is no corner frequency. If you take the first part like 1 plus 0.1 j omega is equal to 0, so what will happen, 0.1 j omega will be equal to minus 1, and j omega is equal to minus 1 divided by 0.1. By taking the modulus, because we need the value one value of omega, so by taking the modulus, the j omega will becomes omega, and the value of omega is equal to nothing but 10. Similarly, the second part, this one, 1 plus 0.001 j omega, when we are making it equal to 0, so it will becomes mod of j omega is equal to minus 1 divided by 0.001, which is equal to 1000 radian per second. So this is for the only purpose of work. You don't mention it in the, if you are not getting remember how to find out this corner frequency. So this is the easiest way to find out the corner frequency. I mean, according to the number of corner frequency, you keep it in the according ascending order, like omega c1, omega c2, and omega c3. So now the third step is the magnitude table. Here the very simple, we'll make a table where we have four terms, like term, number of terms, corner frequency, slope, and change of slope. So how will decide the term? This is the little important part, uh, deciding the terms. So this is the transfer functions. Make it sure that the first term will be always with the this constant, like 1000 or a b c, whatever the terms it comes over here, the first terms will be always included the this constant part. Like if it is 1000, so it will always include this 1000, and along with the individual term of s, like 1000 divided by s will be the first term. Okay. If you are taking this one after putting j omega, so 1000 divided by j omega will be the first term. If there will be no j omega terms here, so the 1000 will be the first term. If this j omega or s terms will be here in the numerator, then 1000 j omega will be the first term. That means with the constant terms, whatever the terms term will come of individual term of s, like s square, as, or sq, that will be the first term. And then after the terms which included the corner frequency, like 1 plus 0.1 j omega, 1 plus 0.0 j omega, so in increasing order only will put this term. So here from this one, the first term will be 1000 divided by j omega, because it doesn't have any corner frequency, I have not, we are not applicable. And the slope will be minus 20. How this slope comes minus 20, I will explain in the later next slide. But you just you have to remember that if there is a terms j omega terms in denominators, so it gives minus 20 dB per slope. If there is a term of omega, j omega, or s in numerators, it gives plus 20 dB per decade slope. So change in slope, I mean there is no change in slope, because we have started the graph from here itself. So the first term doesn't give any change in slope. Now the second term is one second term will be, because this is the comparably first corner frequency, so we'll take this one is first. 1 divided by 1 plus 0.1 j omega, we have the corner frequency 10. Again it also contribute minus 20 dB per decade slope, because the j omega terms is in denominator. So initially the slope was minus 20 degree, and again it contributed minus 20 dB slope, so total slope will becomes minus 40 degree. Many people are confused because the minus 20 dB and minus minus, it becomes zero slope. So don't be confused. It is previously it has minus 20 dB slope, and again it contributed minus 20 dB, so the total slope will becomes minus 40 dB per decade. Welcome back to tutorial video of drawing the Bode plot. So just in previous slide we have studied first two step, and we are discussing here the third step. So here in case of third step, uh, till now we have discussed here, that means the second terms. Now the third terms will be 1 divided by 1 plus 0.0010 j omega. uh, and it has the current frequency 1000, and it contributed slope again minus 20 dB, because here individual term of j omega is there. We do not have to consider the constant terms or any terms which is included here. Only we have looked at that how many terms are there of j omega, or I mean s or j omega, like that. So because you have only one terms in denominator here, j omega, that's why it is minus 20 dB. Previously it was minus 40 dB slope, and now this minus 40 dB, and this term contributed minus 20 dB. Total slope becomes minus 60 dB per decade. Okay, so this is the table which gives you the magnitude, we call magnitude table, or contribution of magnitude table. Now the fourth step is to choosing the lowest and highest corner frequency, or we can say frequency. Now see here, we have only two corner frequency, omega c1 is equal to 10, omega c2 is equal to 1000. Now what we'll do, by our sake, to draw the graph, we'll take the lowest frequency, any frequency less than 10. You can take 9, 8, 7, 5, 4, 0.1, whatever you like. But for the convenience purpose, and making the calculation easy, I have taken omega l is equal to 1. You may take anything, 5, 7, and the graph and your final plot will be same. No changes will be there. And one, the highest frequency, which should have more value than 1000. You can take 2000, 4000, 8000, whatever you may, but it should be more than this omega c2. So I have taken omega as 10,000, so it will be little bit more easier to, I mean, draw the graph. Now the fifth step is to find the magnitude at each frequency. Now I have we had two corner frequency, omega c1, omega c2, and now including this omega l and omega h, we have total four corner frequency. So finding out the first corner, first magnitude at this frequency, omega l is equal to 1. So I will make sure that you have just only remember only two formula. The first one is that magnitude at omega is equal to omega l is equal to 1 is equal to 20 log first term. So what is our first term? 1000 divided by j omega. This will be equal to 20 log 1000 divided by j omega, because we are taking mod. If you are taking mod, so j omega part will become omega, so which will have 20 log 1000 divided by omega l. And now 1000 is equal to 20 log 1000 divided by the value of omega l is equal to 1000 by 1, and it is equal to 60 dB. So the magnitude at omega l is nothing but 60 dB. Next, we are finding out the magnitude at omega is equal to omega c1. The similar formula will be used. I mean similar, this one 20 log first term, that means 1000 mod of first term 1000 divided by j omega at omega is equal to omega c1, and here it is 20 log 1000 divided by 10. So which will be 10 because the omega c1 value is equal to 10, so we have put here 10. 1000 divided by 10, and we have 40 dB. Now from the third, each case, whatever the Bode plot you are going to solve from, I mean the first two terms will have the same formula, and from the second term onwards you have the common formula. From for omega is equal to omega c2, we have the formula slope from omega c1 to omega c2, because till omega c1 already we have found the magnitude. So slope from omega c1 to omega c2 into log omega c2 by c1 plus whatever the magnitude we found out in at omega c1. So magnitude at omega is equal to omega c1. So put this value, slope from omega c1 to omega c2, go to the table, go to this is the value of omega c1, this is the value of omega c2. So between this omega c1 and omega c2 our slope will be minus 40, and between from omega c2 further our slope will be minus 60, and before that minus 40, before omega c1 our slope will be minus 20. So the slope between omega c1 to omega c2 is minus 40 log omega c2 value is 1000 divided by omega c1 value is 10, and plus the slope at omega c1 is equal to 40. So we have minus 8, this becomes minus 80 plus 40 is equal to minus 40 dB. And the final one, again the formula will continue even though you have 5 terms, 6 terms, 7 terms, whatever the terms will be there, it will be similar pattern. You have to write the formula. Slope from omega c2 to omega h into log omega h divided by omega c2. If there is another term like omega c3, omega c4, so we could have kept here omega c2 to omega c3, but here we have the final frequency omega h, so we'll put omega c2 to omega h into log omega h divided by omega c2 plus the previous magnitude m at omega is equal to omega c2. So the slope from omega c2 to omega h is equal to minus 60 log minus 60, because this is from this is the value of omega c2, and for afterwards and after minus sorry omega c2, the slope will be minus 60 only. So this is minus 60 log the value of omega is equal to 10,000 divided by 1000, which will be equal to minus 60 only. Minus 60 and minus 40 we have minus 100 dB. So now we have uh, magnitude at each level. That means at omega h we have minus 100 degree, at omega c1 c2 we have minus 40 degree, at omega c1 we have minus plus 40 dB, and at omega l we have 60 dB. So go to the semi-log graph plot. This is the semi-log graph plot, semi-log graph, where it is divided in such a way that the first will be started with 1 or 0.1 or whatever your value is, and the second thick line is the multiple of 10. That means if we are taking, you consider it as 1, it will become 10, again this will become 100, this will become 1000, 10,000, and 10 1 lakhs, and it goes on. If you are starting with 0.1, the here it will become 1 because you multiply with 10, 1, and the total uh, um, I mean values will be nothing but equal to 10 here. So if you are putting it, like if you are taking the terms, first one is 1, then this one is second, third, fourth, fifth, sixth, 7, 8, 9, and this is 10. After that, after 10 it will become 20, 30, 40, 50, 60, 70, 80, 90, and 100, and then after 100 it is 200, 300, so on. So this horizontal axis will be taking the frequency in radian per second, and this vertical is nothing but magnitude, what we have found. So at the first omega l is equal to 1 we have taken, at omega l is equal to 1 we have magnitude 60, so we'll put here 60. Now how we are going to put this value of magnitude? So you take any point as a 0, like what I have considered 0 here, because here maximum value is plus 60 and minimum value is minus 100. So I have adjusted in such a way that it can be uh, kept 0 to 60 here and 0 to minus 100 here. So and consider 20 dB space between each line. So here why it is called semi log graph, because this is the normal axis and this is the log axis, logarithmic axis. So now put these values in similar fashion what we have found out, like at omega l is equal to 1 we'll put 60 dB, omega c1 will put 40 dB, at omega c2 will put minus 40 dB, and omega h will put minus 100 dB. And one more thing is that this this part, I mean the frequency part, uh, it has to be started with your lowest frequency only, your lowest frequency only. Like if your lowest frequency is 1, you can start with 1. If your lowest frequency is 0.1, you can start with 0.1. If your lowest frequency is 0.01, you can start with 0.01, and then the next line, I mean if you're starting with 0.1, the next thick line will be multiple of 10, that means 0.1110, and it goes on. So this is the term, I mean this is the semi log plot, and in a similar fashion you have to put these values. And one more thing is that this part, vertical part, will always keep for magnitude values, and the horizontal axis will always keep frequencies value. So thanks for watching this in Okay, so welcome back to the tutorial video of Bode plot. So in previous slide we have studied of till fifth step. That means first step s is equal to j omega. We put the j omega and then we found out the corner frequency, and then after we draw the magnitude table. Fourth step, we have considered the lowest and higher frequency. Fifth step, we found out the magnitude at each frequency level, and we have also understand how to decide these values, according to your magnitude as well as frequency. So now we have frequency. I mean this four frequency: omega is equal to 1, omega is equal to omega c1 is equal to 10, omega c2 is equal to 1000, omega is equal to 10,000. And we have also magnitude at omega is equal to 60, omega c1 is equal to 40, omega c2 is equal to minus 40, and omega is equal to minus 100 dB. So let's put these all values in this graph. So this is omega l is equal to 1. And this is nothing but omega l, and this is omega c1, and this one is omega c2, and this one is omega h. Okay, so at omega l our magnitude value is 60. So we have I mean this is the 60 dB. So we have taken here, considered here 60 dB. At omega c1 we found out that the magnitude is 40 dB. So this is nothing but the 40 dB. And at omega c2, that means that 1000 radian per second, we have the value is equal to minus 40 dB. So we have put here minus 50 dB. And the last at omega h we have magnitude value minus 100 dB. So we have taken here minus 30. And now what you have to do, you have just take an scale and join these points. Like the first point you have joined from this to this, that means omega l to omega c1, again omega c1 to omega c2, and omega c2 to omega h. You will find out that your magnitude plot of your Bode graph, and automatically you will find that this is the first slope will be equal to minus 20 dB per decade, the second slope will be minus 40 dB per decade, and the third last slope will be equal to minus 60 dB per decade. You can verify even, because the first value is 60 and it has the decrease of 20 dB per 10 slots. So that's why it is called minus 20 dB per decade. Okay, and uh, in the next slide I will discuss about how this slope is being considered. Like, see here, I mean we have considered terms as well and corresponding their slope. So if you are taking terms like s square, these all terms are in numerators and these all terms are in denominators. So if you are taking any term which like s or g omega, because we are putting s is equal to g omega, it will gives the slope of plus 20 dB per decade. And if you are taking the denominator term, I mean you're not taking, if it's given as s square in terms of s square, so it or g omega square, it will give the slope of plus 40 dB per decade. And similarly if it has the third power, that means s cube, so it will give you the plus 60 dB per decade slope. Even though it, if it is in the terms of like a plus s, a plus s means any constant term, 2 plus s, 3 plus s, even though 1 plus 3s, 1 plus 5s, or a 1 plus as, like that, only we have to look at here the s terms. You do not have to consider any constant or any other terms. If you have any value of s in numerators, so it will give plus 20 dB per decade slope. And if any values it is have a square terms, I mean of s, so it will give the plus 40 dB per decade upslope. And the next one is if the s term is in denominators like 1 by s, 1 by s square, 1 by s cube. So the one s terms will contribute minus 20 dB, and two s terms, that means s square terms, will contribute minus 40 dB per decade, and three s terms will contribute minus 60 dB per decade. Similar fashion, we don't have to consider any constant terms, any other terms. We have to consider only s terms or j omega terms, because only s terms will contribute slope. So here, because there is a 1 divided by a plus s, so there is only s terms in denominator, so it will contribute minus 20 dB of slope. That's why from this magnitude table we have considered here 1000 by j omega, so there is a single omega terms in denominators, it contributes minus 20 dB per decade slope. And the second one, again we have only one terms in denominator of j omega, it also contributed minus 20 dB slope, and so on. So let's go through briefly about that how to draw the Bode plot. So first step, we have taken the transfer functions and put s is equal to j omega, s is equal to j omega uh, in g of s, and then we have started with the magnitude plot. The first step to find out the magnitude plot is find out the corner frequencies, then magnitude table, choose the lowest and highest frequency, then find the magnitude at each frequency. So like s is equal to j omega, we have put here corner frequencies. That way to find out the corner frequency is omega c1 is equal to 1 divided by this terms, that means constant term 10 radian per second. Here omega c2 is equal to 1 divided by 0.01, because we have only two corner frequency. And one important note is that it should be always in the uh, form of 1 plus ts. If it is not, then make it in the form of 1 plus ts, and then find out the corner frequency. The magnitude table, again magnitude table have four terms, a term, corner frequency, slope, and change in slope. The term will depends upon the how many terms it has. I mean, for example, we have only three terms, this constant and this term is considered first term, the second term, and third term, and the terms order will be depending upon the corner frequency. Increasing order will keep this one, and then we'll take the lowest frequency and highest frequency, step 4. So lowest frequency will be always less than your first corner frequency, and the highest corner frequency, highest frequency will be always than your maximum corner frequency. Then we'll find out the magnitude at each level. We have only two formula to find out the magnitude. First one is the 20 log first term, that is for first two term, and from third onwards we have the formula slope from omega c1 to omega c2 into log omega c2 by omega c1 plus the magnitude at the previous values. And then after the semi-log graph plot, in the semi-log graph plot, this is the horizontal axis is the frequency, vertical axis is magnitude in dB. So that's all. And each frequency, at each corner, I mean each frequency, just put the magnitude what you have got and make it a scale with your scale, and you will find out the your magnitude plot of your Bode plot. Now in the next slide we'll discuss about the phase plot, and we'll draw in the same graph phase plot also, and then our complete Bode graph will be over. So hope so you have understand this concept of drawing Bode plot. uh, and if have any queries or any problem in understanding this concept, so you can mail me on this email id harimohanrai@gmail.com, or you can visit my website harimohanrai.wordpress.com. So thanks for watching. We'll discuss further in next slide. Thank you. Welcome back to the tutorial session of Bode plot. So previous section we have studied to draw the Bode plot. The first part of Bode plot, that is magnitude plot. The second part is phase plot is still remaining. So in this session we'll discuss about phase plot, how to draw the phase plot in the similar same similar graph set. So till now we have studied to draw the magnitude plot of Bode graph in a semi-log graph set. So we'll continue from here. Now to find out the phase plot, first of all we find the angle of the given transfer function from equation number one. You see the equation number one, g of j omega. Already we have 1000 after putting s is equal to j omega, and j omega 1 plus 0.1 j omega 1 plus 0.01 j omega. From this equation, equation number one, we'll find out the angle. Angle equation will be g of j omega, angle of g of j omega is equal to minus 90 degree, because 1 by j omega and angle contribute minus 90 degree. 1000 because there is no imaginary axis here, so it does not have any angle. It will give 0 degree angle, so that's why, so no contribution of it. So for this term we have minus 90 degree. 1 divided by 1 plus 0.1 j omega, it will give minus 90 degree 0.1 omega, and for this part it is minus 90 degree 0.001 omega. Now we'll draw a table with this variable, yeah, various value of omega. We'll put the various value of omega here, and we'll find out the angle accordingly. So let's see here the frequency value, omega value we are putting here, like 1, 5, 10, 50, 100, 20, and 500, and correspondingly we are finding angle of g of j omega in degree. So now look at here, if we will put omega is equal to 1, so what will happen? Minus 90 degree minus 10 was 0.1 into 1, minus 90 degree 0.001 into 1, and we'll get angle minus 95.7 degree. Similarly, if we'll put 5 in the previous equation, it will be minus 90 degree minus 10 was 0.1 into 5, minus 9 10 was 0.001 into 5, and will get minus 116.5 degree. So you may consider it is 96 degree, you may consider this one is 117 degree. We'll put omega value 10, then we may get 135.63 degree, that is nothing but you can consider it 136 degree. Similarly, so the confusion and question will come into your mind that how this omega value will be selected. Actually, I'll suggest you to put the omega values in such a way, select this omega value in such a way that the minimum value of angle should be approximately 100 and 110 approx, and the maximum value should be more than 180 degree. It sometimes if will be even though you'll be putting more number of values, then also you won't get 180 degree. So minus 1 degree actually, then in that case you just leave it. Otherwise you select omega in such a way that minimum value should be near about 100 degree, and the maximum value it should be near about 180 degree, more than 180 degree. So this is the way to select the omega value. You put this omega value in this equation number 2, and you get corresponding angle here. Now look at this semi-log graph. Already we have plotted this magnitude plot, minus 20 degree per decade and minus 40 degree per decade and minus 60 degree per decade. So, and we have discussed also how we have drawn this one. Now in the same graph sheet you will draw the phase plot also. So how to draw it? What we'll do, in this side we have taken magnitude in dB, okay, and in this horizontal axis we have considered this is frequency in radian per second. So opposite to this magnitude term, and in this corner what we have done, we have considered angle in degree, okay. Why we have considered this side? Because if we'll put same side, so it will be the overlap of that magnitude as well as degree. So what we have done, we have just considered this side, this corner of semi-log graph sheet as a angle, and it is in degree. So how we have selected this degrees value? So because we have maximum minus 205, that means approx 206 degree, and the minimum we have minus 95 or 96 degree. So we'll substitute such a way that the maximum value will be near about minus 200 and the minimum value should be near about 90. So I had started with minus 220 degree. It will be in negative, because we have all negative values, so that way I will consider here negative, and you just put in a decreasing or like minus 220, minus 200. The Because I have taken 20 degree gap between these two values, just because I have to adjust this all value minimum and maximum. So 220 uh, values, minus 180 degree, minus 160, minus 140, minus 120, minus 100, and minus 80. Now at from this table we see that at frequency omega is equal to 1 we have 95.7 degree, at 5 we have 116.5 degree. So look at here, at 1 we have substituted approx 95.7, that means 96 degree, because this is the 100 and each a small block has a difference of 4. So that this is nothing but 96 degree approx. So at 5, that means 1 2 3 4 5, 5, the angle is approximately 116 degree, and at 10 degree we have the angle approximately approximate to 136 degree. Similarly at 20 30 40 50 we have the angle approximate to 172 degree, and at 100 it is near about 180 degree, and 200 again we have the angle 188 degree, minus 188 degree, and at 220 approximately 206 minus 206 degree. And this graph has to be drawn in a free hand. We are not using a scale here, just because the margin will be increased. That's why we will uh, um, align this all the dotted line with the free hand. Okay, so now this yellow, I mean green line is nothing but phase plot, and this blue line is magnitude plot. I mean a same graph sheet, semi log graph sheet, we have plotted magnitude plot as well as phase plot. Now this complete graph is nothing but Bode plot. So in now there's one more or one or two more terms is there, that is phase, how to find out the phase margin and gain margin. So this 0 dB line I have drawn a red line, and minus 180 degree line here, minus 180 degree line I have drawn with a red line. So because while finding out the phase margin and gain margin, these two lines are very important. So in just I am giving a brief overview. This 0 degree line where it intersects the gain plot, it is nothing but gain crossover frequency, and the minus 180 degree line where it crosses the phase plot, it is called phase crossover frequency. Not clear? And now this point where this 0 dB line crosses the gain um, plot or magnitude plot, this is called gain crossover frequency. Now you just draw a line in such a way that this should intersect the phase plot. So the point where it intersects is the difference between minus 180 degree line to this point is nothing but phase margin. Now opposite to that, minus 180 degree line crosses this one is phase crossover frequency. Now draw this line in a upwards in a such a way that it intersect gain margin somewhere. So the difference between 0 dB to the point where it intersect is nothing but gain margin, because in this case the gain crossover frequency and phase crossover frequency align together. That's why in the both the cases gain margin and phase margin are 0 degree. So that's why because it overlaps gain crossover frequency and phase crossover frequency each other. Thanks for watching, and in next session we'll continue further.